Hey guys, welcome to yet another interesting video on Euclidean geometry grade 11, and for today's lesson we're going to do a proof of theorem number 5. That's about cyclic quadrilaterals. So without wasting much time, let's go straight to the proof. So we've been given a circle with a quadrilateral ABCD, which is, by the way, a cyclic quadrilateral, and we're required to prove that angle A plus angle C gives us 180 degrees. So every time you're given a quadrilateral whose vertices touch the circumference, like as you can see, the vertex here, the vertex here, the vertex here, and the vertex there. So if all four vertices touch the circumference of a circle, it means that that particular quadrilateral is a cyclic quadrilateral. So the word quadrilateral, by the way, is very long, so we're just going to stick to quad for now. So yeah, let's go straight to the proof. So as usual, the first thing that we're going to do right now is to make a construction. So I'm just going to quickly write the word construct. I'm not going to write the whole word. So we're going to say join O to D and O to B. So we're going to join O to D and we're going to join O to B. So as you can notice here, I'm joining O to the angles that are not involved in the proof. As you can see, B and D are not involved in the proof because the proof, because the question wants us to prove angle A and angle C. These are the two angles that are involved. So our construction requires that we join O to the two angles B and D, the ones that are not involved in the question. So after we make our construction, we can now go straight to the proof. So as you can see, we now have angle O1 and we have angle O2. So look at this carefully. Angle O2, this one, is twice the size of angle A. So that's what we're going to start with. We're going to say angle O2 is twice angle A, and the reason will be angle at center is equal to twice angle at circumference. So by the way, this theorem is also another spin-off of theorem number 2. And then, so as you can see, the angle at the center, O2, is twice the angle at the circumference, that's angle A. And then we're going to come back again and say the angle here, O1, this angle right here, angle O1, it is twice angle C. So we'll say again, angle O1 is equals to twice angle C. Once again, we'll say angle at center is equal to twice angle at circumference, like that. So as you can see, angle O2 is twice angle A and angle O1 is twice angle C. Now we're gonna continue with our proof. We'll say therefore angle O2 plus angle O1, when we add this angle O2 and O1, when we add these two angles, you will see that it gives us 360 degrees because it's a revolution. Our reason will be rev, which represents rather a revolution. So with that being said, guys, we're gonna continue. So remember, angle O2 plus angle O1 gives us 360 degrees. Now, if you can check, what was the value of angle O2? The value of angle O2 was 2A, and then the value of angle O1 was 2C. So 2 angle A plus 2 angle C gives us 360 degrees. This is so easy because we've replaced angle O2 with 2A and we've replaced angle O1 with 2C. And then we are going to factorize this now. We'll say 2 as the common factor. Then you remain with angle A plus angle C, which gives you 360. And then we're going to divide both sides by 2 in order for us to get rid of this 2. Therefore, angle A plus angle C gives us, what's 360 divided by 2? Obviously that's 180 degrees. So that's the end of the theorem. We've just proven that angle A plus angle C gives us 180 degrees. Just to track back to what we did, the first thing we did is construct. By construction, we joined O to D and O to B. After doing that, we created angle O1 and angle O2. And then we know that angle O2 is twice angle A, then angle O1 is twice angle C. The reasons being, angle at center is twice angle at circumference. But we know that angle O2 plus angle O1 gives us a revolution. So O2 plus O1, that's 360, that's a revolution. And then angle O2 was found to be 2A plus angle O1 was found to be 2C equals to 360. And then we took out the common factor being 2, then we remained with A plus C equals to 360. We divided both sides by 2, then angle A plus angle C gave us 180. So that's the end of the theorem, and I hope somebody got some help. So what I want you to get from this theorem is every time you are given a circle, so the proof of the theorem ends here. So every time you are given a circle and you are given a cyclic quad, like this, you always have to know that the opposite angles of that cyclic quad, this can be x, y, z, and a w, like that. So you have to know that angle w plus angle y, so angle w plus angle y give you 180. You have to know this whenever you're given a cyclic quad. Or angle x plus angle z, like that, give you 180. So the reason for this theorem is opposite angles of the reason for this is opposite angles of cyclic quad are supplementary. So that's the reason for the theorem. It's simply opposite angles of a cyclic quad are supplementary. every time, guys, they give you this, always write this reason. And yeah, so that's it from me, ladies and gentlemen. If you like this video, once again, please and please and please, I beg you to subscribe to my YouTube channel and ring the bell and share my videos so that you can get the latest content that I have to offer. So thank you for your support and thank you for your time. Until we meet next time. Sharp, sharp.